So I covered liquids in the last part. This is still chapter 8. This is just now solids. I felt it'd be best to split the videos because even though it doesn't look like there's too much content left, there's I think I will be doing a lot of talking, just explaining a lot of stuff. So splitting into 2 videos. Solids. Here we go. The first type of solid we're going to be talking about crystal types is metallic crystals, and these crystal types are usually based on attractive forces between the atoms in the molecule. So, for example, metallic crystals are made by usually they're like metalloids or metals making metallic bonds. So you'll see like aluminum is going to be metallic crystals, zinc, copper, iron, all those metals. Those are they're going to make metallic crystals, and so there's a couple common physical traits that you should know about each crystal type. So metallic crystal, one is going to be high melting point and high boiling point. This is because these are strong bonds. I almost wrote bonds there. Point. And these are strong bonds, and yeah, so they're just pretty strong bonds. They're just strong elements, and they just tend to, yeah. So there you go. And yeah, metallic bonds very strong. So that's why the melting point's so high. Also, I mean, if you want to just compare this in your brain, think of the melting point between, like water, which is going to be like 32 Fahrenheit, and then the degrees Fahrenheit, and then the melting point of like steel, you're going to have higher than 1,000 degrees Celsius for their melting points. Alright, well, the second big trait is that they conduct electricity very well. So this is because metals have what's called a loose electron C. It's the valence electrons in a metallic bond. Instead of just bonding around the one atom, they just tend to flow loosely around like the whole solid in a way, or they're just very far away from the metal atom itself, and they just mix, and then because of the distance, and so this is called the mobile valence electrons, or the electron C, and this allows electricity and heat. So I'm going to make that clear. Alright, so heat and electricity allows it to conduct very well through metals. That's why you have iron frying pans. Also, their high boiling point makes it pretty convenient. And that's why you have copper wiring. It's because they conduct electricity well because of their electron C. So there you go. Now, softness, brittleness, this will come up in the other crystal types. Metals, it depends on the metal. I mean, things like gold, sodium, potassium, those are pretty soft. You can cut them with a knife, but like zinc, it's pretty brittle. But most metals are malleable, so I'll put that there. Malleable, and which means they can be formed into various shapes with a hammer, or means they can be turned into wires, which is really ductility. I'm not sure why the Barron's book doesn't differentiate, but put plus ductility because that way you know. That's what that means. And so, the properties of metallic crystal, those are the 4 big ones you need to know. Is high melting point, conducts electricity well, conducts heat well, malleable and ductile. So, strong bonds, metallic crystals. Next one's going to be ionic crystals. Alright, so ionic compounds, or ionic crystals, sorry, they're formed between the attraction, we've been over this before, attraction of the positive cation and the negative anion. So common examples include sodium chloride, just things like that, really. Sodium chloride and lithium fluoride, hydrogen chloride, all that good stuff. Anyways, actually not hydrogen chloride, take that back, I think. Anyways, so a lot of salts. Most salts are going to be ionic crystals. Once you learn acids and bases, that's something you can look at. So they have a couple physical traits also. So first, strong bonds. They have very strong bonds, especially compared to other elements or other molecules with relatively similar molar mass. So that's when metals, you see like they're super strong, but they also have really high molar masses. Well, NaCl has a pretty low molar mass. Anyways, moving on. Because they have this high amount of strong bond, they need a high amount of energy to separate the ions, also called lattice energy, which will separate the ions into the positive cations and the negative anions, instead of just having an ionic crystal. So if you put enough energy in NaCl, I'll put big E for energy, you will eventually get Na plus and Cl minus. So ionic crystals, they have very regular structure, and they alternate positive and negative ions. Not too much stuff you need to know there. Well, another thing you should know is they only conduct electricity as liquids. Well, or I should say, or aqueous. Some of you are probably like, well, that's weird. Well, let's say you melt NaCl. That's enough energy for lattice energy. Splits the ions, and ions conduct electricity very well. When NaCl is added to water, the high polarity in the water, the dipole, well, NaCl is also very polar, has a lot of charge, because it's ionic, right? It's going to have charge, so you get an ion dipole attraction between the water and the NaCl, and the like polar substances do in water, because like dissolves like, the water will dissolve it, and it will dissociate into Na plus and Cl minus, which are ions that conduct electricity, which will make the water conduct electricity, which is why salt water conducts electricity a lot better than just pure distilled water. So there's that. It conducts electricity well. However, ionic bonding, brittle crystals. Not like the metal where there's kind of a mixed bag. These are all pretty brittle. If you think of salt, it's like brittle. I mean, it's kind of sandy. Other than that, I think that's pretty much it for ionic crystals. Yeah, that is pretty much it. So we're going to move on to molecular crystals. So molecular crystals are composed of atoms of the nonmetals or of covalent molecules, and they're usually held together by they're always held together by either London dispersion forces, dipole-dipole attractions, hydrogen bonding, or a mixture of these. So this is when you start to see, this is where like all the organic chemistry falls in. You start seeing methane, ethane, propane, butane, and so on and so forth. That's going to be 10. Alright, anyways. So that's when you start seeing all these, and then all the alcohols. So you might get like ethanol, C2H7OH, I think. It's been a while since I've had chem. I haven't really refreshed yet. Yeah, I think that's right. Whoop. That shouldn't be a 7 on the end. That should be an H. What was I thinking? Anyways, so that's what molecular crystals are. Just pretty much, yeah, they're just atoms of the nonmetal variety or covalent molecules, and they're crystals though. So these things, and they're held together by London forces, dipole-dipole attractions, hydrogen bonding. So those forces. Alright, so because these are forces that are much weaker than like ionic bonds or metallic bonds, these crystals are soft. They have a low intermolecular forces, so they have a low melting and boiling point. They also, well, they're just not like superpolar or anything, so they don't even really conduct electricity well. So there you have it. I think those are the two ones that you need to know for molecular. That they're weak, they have low boiling points. Yeah, that's pretty much it. Yep, that's it. So as you might guess from covalent crystals, they are crystals that are formed by atoms that covalently bond with each other. So the result is the crystal is just going to be one big molecule as just a continuous chain of covalent bonds. So things you might see is like diamond. It's going to be like all carbon. You get they each have 4 bonding sites, right? So you'll see carbon is bonded into infinity. I'm sure at some point they start bonding with the other carbons around them like that to make the diamond not go on for forever. But I'll just get rid of that there. That should be enough room to write. Alright, well, covalent crystals are So now we're talking about amorphous substances. These are some materials that they just don't form crystals. Well, one characteristic is that it does not have a distinct, that was a horrible dot, no distinct melting point. As you can imagine, because it doesn't make a crystal, it's hard for the whole crystal to melt together if it's not a crystal. So, no distinct melting point. Just some of it melts sooner than other because some of it will be bonded over, some of it's going to be bonded better than other portions of the amorphous substance because it's not regular crystals, it's very irregular. Yeah, they're not arranged in a network, so no distinct melting point. There's not much more. The book says about amorphous crystals, and it's for a good reason. They don't show up ever. Another thing that came up on my test were irregular crystals, and these are probably pretty similar to amorphous in what they are, but they're crystals that just didn't form properly because the materials or the molecules were cooled, like were heated and then cooled too fast, so they didn't have time to align properly before becoming a solid. Another thing that we learned about when I did it, but also never came up, was there's a certain type of crystal, and it's just created from like freezing noble gases, I believe, and it makes a very weak crystal. So again, that will probably almost likely, or yeah, I imagine that would never show up on your AP test. So don't even worry about it. It's why I'm not teaching it, and it's why it's not in the Barron's book. Moving on. This is a phase change diagram. This is if you had science in middle school, this probably looks pretty familiar. If not, don't worry about it. And explain all of it. Probably looks a little weird because of all the plateaus. Well, what's happening is heat's being added to a substance. Well, as a molecule changes phases, liquid to gas, solid to liquid, liquid to gas, the temperature stops going up. Temperature is defined as average kinetic energy, really. It's a way to measure it, combined with, I think entropy. You don't need to worry about entropy right now, but just think of it as average kinetic energy. As the heat is added, the temperature goes up originally. Well, right here, this guy, if this is a solid right now, this is its melting point, right? MP. Well, at this point over this plateau, you see that there's still heat being added because it's moving along the x-axis, but there's no temperature going up because it's not moving along the y-axis. Well, what happens here is the solid is turning into a liquid because, well, the temperature doesn't go up because the molecules are turning the heat that would have gone into temperature into energy to split apart from its crystalline structure. So there you go, solid to liquid. Alright, well, now we have another plateau, right? Well, you probably figured out this is as a liquid, and then right here it's going to be boiling point. So again, another plateau. The temperature is not going up because the energy isn't used to increase the average kinetic energy. The temperature is used to break bonds and split the liquid molecules apart so it can become a gas. So we get L to G, and then we'll have just G. And then the heat just goes up because the gas just gets hotter and hotter. I mean, eventually it'll probably turn into a plasma, but that's going to be in a super extreme heat, and you do not need to worry about it. Alright, well, the book talks about it. I personally would not mention it right now, but because the book talks about it, I'm just going to mention it. Sometimes when you heat something up, you might get a little bump in your phase graph, so that instead of making a nice point and plateauing, it might go up, make a little hump, and then plateau. It'll also probably happen up here, if it does happen. It's called superheating, and it's just when you heat a molecule up faster than it has faster than it breaks its bonds. So the temperature actually goes up because it's not breaking its bonds even though it's beyond its normal melting point, and then it goes back down as that energy that increased the temperature is used to break bonds. So you can get some superheated liquids this way. Also going back down the opposite way on the phase change, you can get super cooled liquids, and they usually they're both usually pretty violent like liquids. They bubble a lot and they're rapidly phase changing, which is how you get irregular crystals, super cooling. So not super important. I never had anything on it on my AP test, but personally I think it's pretty interesting. So I mentioned that. There you go. That's how you read a phase change graph. Constant amount of heat and temperature going up that way. Alright, well the book also has an example of a phase change diagram of a gas cooling into a solid. It pretty much just looks like the opposite of the one I just showed. So I'm not going to draw it. You can figure it out on your own, I'm sure. But if you want to see it in the book and you have the same edition, it is on page 308. But I'm going to do phase diagrams. Now this guy is probably going to look a little weird to you at first. Stop opening things. iPad. Alright, it's going to look a little weird to you at first, but once you get used to it, it will just make a ton of sense. So this is your axes over here. Now we're going to have temp on the x-axis this time. And what we're going to have up here is pressure. This is because this graph is going to deal with gases. So you're going to get a line. First they're going to tell you it's a chemical, and you're going to get a line something like this, and then you have a big old dot here. I'll use different color. And a line going up that way, maybe a little more slanted-y. I'll try to kill some of that, and then probably a line going up like that. Alright, so and this is going to be 1 ATM right here, so you might get a little lines. They don't always have that. It's just there because 1 ATM's common. It's the normal boiling point, and etc. So sometimes they mark it. So I'm also going to label the sections of this graph. So bear with me here. It's going to get probably a little weird at first. So this is a solid. This is a gas. This is a liquid. So, alright, along this line right here represents the different combinations of pressure and temperature that will keep a solid and in perfect equilibrium turning into a gas. So the chemical reaction there will be solid gas, and it'll be in perfect equilibrium. This is when a solid turns into a gas, it's called sublimation, and when a gas turns into a solid, it's called deposition. You won't see that too often, but it's good vocab to know for this. So let's say this is I don't know. Let's pick just a point like right here. So this point occurs at 60 degrees Celsius, and let's call that 0.5 ATM. Well, that line is telling you that at 60 degrees Celsius and 0.5 ATM, the solid of this chemical is going to be perfectly in equilibrium with the gas form. So it's going to be turning into gas as fast as the gas is turning into a solid. An example of solid to gas that you probably all know is dry ice. Super cold, and when you open it, it's such a temperature shock that it changes right into the CO2. Anyways, if the temperature were to say go up 80 degrees Celsius, but we stay at the same ATM, you see that the point moves over, right? Well, that tells you that at 80 degrees Celsius and 0.5 ATM, this chemical is a gas. Well, this goes up to 0.75, and we're still at 60, and you see it's a solid. Now, if you remember, the pressure will force the molecules of the gas together until they're going to be touching. So a high pressure will turn a gas into a solid or a liquid. So just like that line, this guy over here, this is the line. It's going to represent vaporization and condensation. So that point there, there's going to be an equilibrium between solid and liquid, and down there's an equilibrium between liquid and gas. I'm sorry, not vaporization here. Here is a melting and freezing. Here is vaporization and condensation. Well, as you can read on our graph, if I told you, hey, at 2 atm, we'll say that's there, and at 160 degrees Celsius, we'll just say that's there, what type of what state of matter will it be? Well, go over to or up to over 160. The line doesn't really cover, but that looks like it's going to be a gas. However, also might not be a gas. We have something here. This is the end point on this guy. It's called the critical point, and this is when that is the maximum temperature that any liquid can exist. So it doesn't matter what the pressure goes up to. The pressure can go up to like 8,000 atm, but at 160 degrees Celsius, this chemical will always be a gas. So I'm sure I explained the first line in depth pretty well. You can probably carry that over to the other lines, but I'll just do a quick example. If you know that that's at 80, and we'll say that's at 1.5 atm, it's going to be in perfect state of melting and freezing, where it melts as fast as it freezes. But if the temperature, say, went up 10, then it becomes a liquid. If it cooled down 10, then it's a solid, right? So there you go. It's not too hard of a table to read. I just have one more point to go over with you on this table, and then we're done, I think, with this whole chapter. So this guy right here, this is called the triple point. Now, if you've learned anything from the lines, you can see that all three lines intersect here. Well, what do you think that means? That means that this molecule, this poor molecule, is turning into liquid to gas and liquid to solid. Whoop, those are both the same way. Liquid to solid and solid to gas, gas to solid. This is all happening perfect equilibrium. So it's the substance is going to be equal amounts solid, liquid, and gas, because it's all changing, phase changing as fast as molecules are changed to it. So pretty crazy point on the graph. You don't see it happen too much in practice, but you probably will be asked to draw a graph of a chemical given some data and then asked to find the triple point, or you might be given a graph and asked to find certain points on the graph. Or you might be given a graph and you might be given, hey, I'm looking at 100 degrees Celsius and 2 atm. What state of matter is it going to be? So those are the type of questions you will be asked on the AP exam, and probably exam given by your instructor, if you have an instructor. Also, I'm sure as you all know by now, Barron's book is just full of good tests for you to take. They're practice tests. They're usually a little bit harder, I think, than the multiple choice on the AP exam. And also they might ask you some weird questions that you don't think was very covered very well in the chapter, but that's just the nature of the game. So there you go. Important concepts for this chapter were intermolecular forces like dipole-dipole, London dispersion, and hydrogen bonds, physical properties and intermolecular forces for liquids, and solid crystals and crystal structures, and then the heating, cooling curves, and the phase diagram, which I just drew. So there you go. That's Chapter 8.